The fastest bomber on Earth shouldn't exist anymore, and yet it just got faster and flies farther. The Tu-160 earned the White Swan nickname for its anti-flash, weight, and agility. But the real story is the Tu-160M update. NK-32 Series 2 engines, avionics overhaul, and extended range. It's not a museum piece. It's a cruise missile carrier built to outrun response timelines and refuel to keep pressure on distant theaters. We'll connect its 18,000-kilometer patrol record to why modern planners still budget for a small, maintenance-heavy fleet. Before we move on, please take a moment to subscribe to the channel and like the video. The common line in Western commentary says the Blackjack chased the B-1B into stealth and then missed the turn. The brief did not read that way. The late 1970s specification rewarded speed, altitude, and reach in one platform that could lift a heavy cruise missile load, live through a nuclear environment, and shorten an opponent's decision window. It was therefore not a stealth race so much as a time race. The objective was deep continental strike with weapons on board at rollout, a climb to height, and a supersonic dash to a standoff release line before the intercept chain could fully assemble. So the requirement locked in several concrete features: high subsonic cruise to conserve fuel across intercontinental legs, and a sustained supersonic segment to compress reaction time, blast survivability in structure and systems, plus crew protection choices that show up in the finish and in the compartment design, and a doctrinal pairing with long-range cruise missiles to keep the aircraft outside the thickest radar and SAM belts while still threatening critical targets inland. Western discourse shifted toward low observability in this period, but Soviet planners doubled down on variable geometry and raw thrust. That choice looks contrarian until you weigh the air defense model they planned against. The threat was a layered belt of early warning, look-down/shoot-down fighters, and long-range SAMs that needed minutes to queue and commit. If you compress those minutes, the geometry favors the attacker. The analogy is simple. You can sneak past a guard with a smaller shadow, or you can make the hallway shorter so the guard never gets there. The airframe logic reflects that calculus. A titanium main beam carries wing pivot loads, and major subassemblies tie into a single-piece fuselage integration to keep bending and torsion within limits at high dynamic pressure. The wing sweep ranges roughly from 20 degrees to about 65 degrees. At low sweep, it carries lift efficiently at heavy weights and high subsonic cruise. At high sweep, it reduces drag and structural loads during the supersonic dash. Intake geometry and engine placement follow from that, so the engines keep breathing at Mach, and the wing still produces manageable trim and stability across the sweep envelope. Crew protection shows the doctrine plainly. The anti-flash white finish reflects thermal radiation from a nuclear burst. It is a thermal management choice, not a parade paint scheme. Inside, the crew of 4 works behind systems designed to keep them functional after a flash and through turbulence and shock that follow a near-surface detonation. 0/0 ejection seats add a safety margin across the envelope. Weapons carriage drove the survivability model further. Early integration of the KH-55MS meant up to 12 cruise missiles inside 2 bays. The result was a standoff launch concept that made penetrative stealth less urgent. The missile would do the penetrating at low altitude and long range, while the carrier used speed and altitude to reach a safe release point in time. Automation supported this at workload level: fly-by-wire, integrated navigation and attack systems, and onboard ECM kept the jet on schedule and within parameters during the fast segments. But the 1980s electromechanical displays limited situational awareness compared to later glass cockpits. Data came in discrete pieces rather than fused views. So the crew managed more mental integration, especially during long sorties and complex routing. So, what made the USSR prioritize supersonic speed over stealth? Anticipated NATO air defenses, the desire to outrun interceptor chains, and cruise missile standoff tactics. Mini payoff: speed plus standoff built an alternative survivability route, time compression instead of signature reduction. By this point, the Cold War ended, but the airframe survived. The next problem was straightforward and expensive. Turn a fast, heavy 1980s missile carrier into a precise, networked platform without changing its basic aerodynamic logic, and make engines and avionics built for one war relevant in another. So the obvious question now is how a cockpit full of 1980s switches and 4 thirsty engines turns into a 2020 standoff system that can pressure theaters 18,000 kilometers away without ever crossing a border? The answer sits at an inflection point where propulsion and electronics change the envelope while the airframe keeps doing what it was designed to do: climb fast, cruise long, and get to the release line on schedule. The NK-32 Series 2 and the avionics overhaul mark that break. Institutional commitment shows up in two concrete moves: a contract for a first batch of Tu-160M aircraft and a first flight of a serial production Tu-160M in January 2022. That is how you keep tooling warm, suppliers engaged, and a complex bomber line viable long enough to deliver upgrades into the 2020s force. But the program carries friction. The fleet is small, maintenance is heavy, air defenses have better sensors, better networking, and longer sticks. So the tension is simple enough. Can modernization move faster than obsolescence if you don't change the signature in a fundamental way? The bet is that speed to the launch point and range from it still matter. Unpacking the engine first helps. The NK-32-02 improves efficiency and reliability. That means less fuel burned per unit thrust across long cruise segments, more predictable time between overhauls, and practical gains that show up as longer time on station near the release arc and fewer tanker brackets. If you cut the number of refueling events on an intercontinental profile, you remove failure points and scheduling bottlenecks. When the dash segment still needs a lot of thrust, the engine gives you that margin without crippling the rest of the sortie. The avionics refresh closes the other gap. Modern navigation, radar, and electronic warfare systems improve how the jet plans, updates, and protects its route, and how it employs long-range cruise missiles like the KH-101 and KH-102. Higher fidelity targeting inputs, better route optimization, and more resilient ECM let the crew handle complex airspace and keep separation from threats while staying within the weapon's launch parameters. You get more credible standoff because the guidance chain from aircraft to missile starts cleaner. Operationally, we've seen endurance and signaling wrapped together. An 18,000-kilometer patrol and a 23-hour flight align with the claim that the platform can persist over vast arcs and still present a launch problem to an opponent. The Syria 2015 strikes showed a precision standoff use case for the KH-101, which matters because it links legacy airframe performance with modern weapon accuracy in a real theater. Addressing the payoff directly, the old cockpit limited integration. Electromechanical displays delivered siloed data, which constrained precision and trimmed multi-mission flexibility since crews had to fuse cues mentally. The M upgrade lifts that ceiling. More coherent displays and systems integration reduce workload at the edges of the envelope and during long sorties when fatigue drives error. A small but important enabler is the hose and drogue refueling probe. That hardware gives planners more options because you can match tanker availability across different bases and routes, which is useful when projecting power into the North Atlantic and the Pacific arcs where basing is thin and weather is unforgiving. Fewer hard basing assumptions means more credible deterrent patrols. Few airframes, each with longer legs, better fuel use, and higher quality targeting, can hold distant nodes at risk on predictable timelines. High-speed ingress to a release point compresses an opponent's warning and response cycle, even if the bomber never crosses into the densest defenses. One way or another, the Tu-160M remains a missile truck. The lever arm is longer now, and the engine that pulls it wastes less to get there. The airframe that started as a time compression tool has found a second life doing the same job with more precise instruments. The second life of this airframe trades signature reduction for time compression and reach. New avionics and NK-32 Series 2 engines turn speed and range into deterrence by moving the launch point sooner and farther, which keeps the missile truck relevant without pretending it is invisible. So the question for budgets is blunt. Do a few high-speed standoff platforms deter as effectively as larger stealth fleets? If you had to pick one metric to fund first, signature or response time, which buys you more credible warning compression? Next, we can examine how anti-ship loadouts and new materials might shift that arithmetic again and why planners care.